So here we are back. We're still kind of lingering in section 4.1, looking to supplement and maybe expand a little bit on those concepts. So let's go for it. All right, so the definition of probability, this is what we had previously. Proportion of times the outcome occurs in a very, very long series of trials. I'm going to propose that we maybe change that a little bit. The idea is still the same, but mathematically it would be better just to look at it, say, as the number of times the event occurs, whatever event you're interested, that's out of everything that can happen, which would be successes over total. All right, another thing that we talked about was law of large numbers. And again, that's just if we do something many, many times, the proportion of desired outcomes will approach its probability. Let's see if we can get this to work on an applet. So let's let that open. Okay, so this is coin tosses. And if we were to toss a coin and we were interested in the probability of heads or the proportions of heads that we would get, this is set up for 15 proportions. I'm going to show the true probability line, which is that green line right there. And that way we can see if our tosses start approaching the true probability for flipping a coin and getting heads, which is 0.5. So we'll toss it 15 times. And you can see the variability that we're getting. It started out pretty low. Then it shot up pretty high. It's coming back down. So we can toss it 15 more times. You can see a running proportion here for heads and tails. And we'll just see if it keeps approaching that true line. Now we haven't really flipped it too many times, I guess 45 times. So let's bump this up and let the process go much quicker. Let's go with 200. Okay, see how it's going down to that line? It's still kind of, what's the word I'm trying to think of? Oscillating, vacillating around that line, but you can see it is approaching 0.5. And now we're up to, what? This is going to be 400 some odd tosses. We'll just keep going for a few more times. Now remember, the long run would be what we would want to run this experiment for, and that's, in theory, indefinite. So at least you can see that it started out pretty much displaced from the true proportion, and now it's kind of hanging out around it. See, it's getting closer and closer and closer. I think you probably get the idea. So let's go ahead and retire this and move on with what we have to talk about. All right, so another way to say law of large numbers, if you repeat an experiment indefinitely a large number of times and average the result, which we were just doing, although it was a simulation, what you would obtain should be close to the expected value or true probability. All right, so there's the law of large numbers. Now, we had mentioned this idea of law of averages. It actually wasn't in the notes formally, but it is showing up in homework and in other questions. So here it is. Now, the law of averages is applying the law of large numbers inappropriately to short-term outcomes. It's the belief that outcomes which haven't occurred are due to occur. It's applying the law of large numbers mistakenly when the numbers are actually small. So when you have a lot of births, you would expect to get half boys, half girls, or pretty close to it. That's after observing a lot of births, an indefinite number of births. What if you are, say, having 4 kids, and, well, let's say 5 kids, and the first 4 of them were all girls? Does that mean that you have a stronger chance that the last kid you're going to have is going to be a boy just because those 4 girls showed up? I don't think so. So law of averages lends itself to this idea of a gambler's fallacy. Fallacy is just means, it's a term that says it's a belief that you hold on to and it's really not true. So the gambler's fallacy, that's believing a losing streak will even out in the end. Now this is a great thing because a lot of gamblers really believe this. And so if they go to a casino and they're playing the slot machines or, shooting craps or whatever it is they're trying to win at, and they just go through a losing streak, a lot of them are going to mistakenly think, well, things are going to turn my way because of this law of averages. It just can't be this way forever. Well, actually, it can. It may not be likely in the long run, but just remember all of the games in a casino, all gambling activities are really slanted against you. The chance of you winning, being better than the house winning, it's never going to happen. Now, you can win, and you have to be able to win at some point, because if nobody won, nobody would go to casinos. So somebody has to win, and even win big, so that the belief of a quick and easy payout is what gets people playing. But if you are in a losing streak and you just think, well, I need to play again because this losing streak is due to end by the law of averages, yeah, I don't think so. So that's your law of averages, in case it should show up. All right, so the last thing I want to do, this is kind of, I think it'll be a pretty short video, is look at simulations. And this is using random activities to model chance behavior. Rolling dice, flipping coins, using technology. All right, so when you do that, what you're trying to do is model something that can happen in real life where you won't have to sit around drumming your fingers waiting for it to happen. Like going to a hospital and just waiting for kids to be born. Yes, probably every day a kid will be born. But if you're looking for a group of 500 kids in order to figure out some, idea of probability for some event, then you could be visiting that hotel day after day after day. So the steps are: state what you're simulating and why, plan a workable way to conduct the simulation, run the simulation, state your conclusion. Okay. So what we're going to do is look at two simulations. What is the chance of having your first son by the third of 4 births? In other words, you get 2 girls and you could have a son on the third one and then a girl on the fourth, or you could have 2 girls and then 2 boys, just so long as you get your first son at the third birth out of 4 kids. All right, so we're going to do that by flipping coins. And then we're going to look at one of the problems on your 4.1 review. That was the one about a local charity, and you had to roll 10 die. And somewhere among those 10 outcomes, you had to have all the numbers 1, 2, 3, 4, 5, and 6 represented. In other words, you couldn't be missing a 4 or a 2 or something like that. So, having said that, let's go ahead and start. Here's the simulation for having the first son by the third of 4 births. So here's the plan. I'm going to flip 4 fair coins where tails represent girl babies and head represents boy babies. I'll repeat the simulation 100 times, which I won't make you sit through, and record the number of times the coins come up either tails, tails, heads, tails. See, right there is the third, the third birth is a boy, right there. Or tails, tails, heads, heads, where the third birth is also a boy. It doesn't matter what the fourth one is. So let's go ahead and let me clean that out. I've set it up to where we can do this online. So I've got 4 coins. Right now it's set up girl, 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 boy, which would be a failure. But I haven't really started it yet, so let's go ahead and go. All right, that's going to be a boy on the first birth, and that's not what I want. So I'm going to put that under a failure. Okay, and then go back, and here we go, and try again. All right, 2 boys. I needed my first one on the third birth. See what I'm doing here? So that's not a win either. So another failure. Okay, and going back, let's try again. All right, that's a boy on the second birth. This doesn't look like this is going to happen too often. So let's mark that as a failure. And I'll do it a couple of more times with you watching before I just kind of leave and do it on my own. All right, what? Okay, girl, girl, boy. All right, that is a success. So I'm going to record that under my successes right here. And then I'm just going to go back and see what I'll get for the next one. I don't know why it stacked itself like that. 6 coins, it's not what I wanted. All right, that's a failure. So let's go ahead and pause, and I will get back to you with the results. All right, so I plowed through all 100 coin flips, and here are my results. It wasn't really that common to see your first son born by the third birth. I had 12 successes and 88 failures. So let's just go ahead and say that the probability of your first son by the third birth, or let's just say at the third birth, maybe that would be a little bit more accurate, at the third birth, that's going to be 12, approximately 12 out of 100, which 6 out of 50, or 3 out of 25. And so if we go to a decimal on that, that's approximately 0.12. So there's that simulation. So let's go ahead then and move on to the second simulation. All right, here we go with the second simulation. You may recall this problem from the time we were doing the review before the quiz, and I told you to skip this one because you had not done the calculator simulation for it before, the random integer. So I'm going to go ahead and run this now with you watching, and maybe you can pick up and use that random integer feature in future simulations, because it's really not that hard. So the problem, if you'll recall, was that a local charity was running a casino night fundraiser, and they had a game called Roll 'em All, and it pays out $5 on a $2 bet. So the player pays $2 to play with a chance of winning $5 back. They'll win if a player can roll 10 fair dice and have all 6 numbers show up. All right, so in other words, of those 10 dice, you'll have a 1, a 2, a 3, a 4, a 5, and a 6, maybe more than one of those, but each one of those numbers has to be represented. So you cannot have 10 numbers, but 4 doesn't show up, or 2 doesn't show up. All right, and this game is played, if this game is played 1,000 times, should the local charity expect to make money on this game? Okay, I'm not going to roll or simulate this 1,000 times, all right? I've got a life too, so I'm not doing that, but I will do it 100 times. And what I'll do is I'll see how often the player wins, how often the charity wins, figure out the money, who gets what, and see if this charity actually can pull off a profit. We're going to use the calculator, so I have the emulator. There it is. All right, I'm going to go ahead and just go with the calculator page on the scratch pad. I'm going to hit enter, and what I want is random integer. So I'm going to do menu, and then choice 5 will be probability. And you see number 4, it says random. We'll go ahead and pick that, and we want random integer. Okay, up this comes, and it wants 3 numbers. It wants to know where to start. So on a die, the lowest number is a 1. So 1, and then we need a comma. The highest number is 6, so it'll generate numbers from 1 to 6. And each time we ask it to run this simulation, we want it to produce 10 numbers. Now that's the hard part, because from here on in, once I hit enter, see I've got a 1, a 2, a 3, a 4, a 5, and a 6. So here, that player won. So I can come back here, and the player won. So I'll put a little mark right here for the player. Okay. Now we'll go back and we'll just do another simulation, and all we have to do is hit enter, and it'll just repeat that command that I put in. All right, so we have a 1, a 2, a 3, a 4, a 5, and a 6. So the player won again. All right, so we'll give that person another mark. All right, so far things are looking good for the players. So we'll do another simulation. Okay, not so good. 1, 2, 3, but is there a 4 in here anywhere? I, for one, can't see it. So that's 1 for the charity. So we'll mark 1 for the charity. Now this is just going to go on and on. I've done 3, so I need to do 97 more. What I'm going to do is do that 97 and get back to you so you don't have to sit through it. So here I go. So here's the outcome from this particular situation. I had, out of 100 games, the players won 33 times and the charity won 67 times. Well, the charity didn't win. The player lost 67 times. So what it turned out, if you had to think about it for a minute, each player played $2 per game, and there were 100 games. So $200 down here went to the charity. Now what did the charity pay out? Well, they had to pay out $5 for 33 winners right here. So that came to $165 that they paid out. So in the end, the $200 that they collected, they returned $165, which means that they made a $35 profit, at least on these 100 games. I don't know, we would have to repeat this over and over and over again to figure out what we would see as the true payout or the true profit that they would make on this. But that's pretty good estimation given that I did 100 trials. So there it is. There are your simulations. I hope you found them to be interesting. We could have actually, while I'm thinking about it before I close out, we could have done that simulation for the boy being born on the 3rd birth. We could have just gone ahead and done probability, random, integer. We could have just said, all right, 0 to 1, 0 being the girls, 1 being the boys, and we want 4, and just hit enter. All right, that would be boy, that would be boy, girl, boy, boy, which is not the first boy on the 3rd birth. That wouldn't win, that wouldn't win, that would win. All right, there's your first boy on the 3rd birth. So there's a lot of ways to run these simulations, and I hope that you found all of this to be sort of interesting. We're going to move on to 4.2 and kind of highlight some of that stuff. So, having said that, thanks for watching. See you next time.